For our network topology, we use DNS-tree to simulate Skynet's autonomous system and its connection to two different internet service providers. Skynet operates under AS65010, which consists of two internal routers, R1 and R2. These two routers are connected to each other through an internal link that runs IBGP, allowing internal route sharing within the same autonomous system. R1 is configured to pair with ISPA, which belongs to AS65020 using eBGP. This connection represents Skynet's first external internet connection. Similarly, router R2 is configured to pair with ISPB, which belongs to AS65030, also using eBGP. This provides Skynet with a second external connection, improving redundancy and connectivity. In addition, an internal LAN interface is connected to the Skynet network to simulate an internal user network. This LAN represents Skynet's internal hosts that rely on BGP routing to reach external networks through R1 and R2. Overall, this topology demonstrates the use of IBGP for internal routing and eBGP for external communication with multiple ISPs. For the IP addressing plan, we assign IPv4 addresses to each router interface based on their roles in the network. For R1, the interface fast Ethernet 00 is configured with the IP address 10.10.10.1. This interface is used as the internal IBGP link connecting R1 to R2 within AS65010. The fast Ethernet 10 interface on R1 is configured with the IP address 172.16.11. This interface is used for the eBGP connection to ISPA, which belongs to AS65020. For R2, the fast Ethernet 00 interface is assigned the IP address 10.10.10.2, which connects to R1 and completes the internal IBGP link within Skynet's autonomous system. The fast Ethernet 10 interface on R2 is configured with the IP address 172.16.21, which is used for the eBGP pairing with ISPB in AS65030. For Skynet's internal network, we use the LAN subnet 192.168.10.0 to represent internal users and services. Additionally, we configured a static route to null zero using the command iproute 192.168.10.0 255.255.255.0 null 0. This configuration is important because it allows the LAN network to be advertised via BGP while preventing routing loops or unwanted traffic forwarding. Overall, this IP addressing plan clearly separates internal IBGP links, external eBGP connections, and the LAN network, ensuring stable and efficient BGP routing. On the ISPA router, the fast Ethernet 00 interface is assigned the IP address 172.168.10.2, creating a point-to-point eBGP connection with R1. On the ISPB router, the fast Ethernet 00 interface is configured with the IP address 172.168.22, forming the external eBGP link with R2.
Hello, my name is Nisa. On this slide, I will explain you how to configure IBGP and eBGP pairing. On the left, we use the command show IPBGP on router 1, ID 172.168.16.11 to verify its BGP table. It has learned the 192.168.100 network. On the right, we see the same for router 2, ID 172.168.16.21, showing it is successfully pairing and sharing router. Next, we verify pairing for our ISP. On the left, ISPA shows a valid path to the 192.168.100 network via R1. On the right, ISPB confirms its path via R2. This confirms our internal pairing is active. To check the health of these connections, we run show IP BGP summary. On R1, we see active neighbor at 10.10.102 and 172.168.1 2. On R2, we see neighbor at 10, 10, 10, 1 and 172.16.22. The up or down column shows the session have been established from several minutes. Checking the ISP site summary, ISP-A is successfully connected to R1 and ISP-B is connected to R2. Both ISP are retrieving prefix, confirming that our network is properly advised the sync routed to the outside world. Now, we look at the actual routing table using show IP router BGP. Currently, both R1 and R2 show that the gateway of last resort is not set, but they are prepared to handle BGP traffic internally. On the ISP router table, we see the specific entry to our 192.168.100/24 network. ISP-A reached it via R1 and ISP-B reached it via R2. The B code at the start of the line confirms these are IGP learn router. We verify connectivity with ping. On the left, R1 successfully pinged R2 at 10.10.10.2 with a 100% success rate. On the right, we confirm the return path from R2 to R1 also fully operational. Finally, we test the internal link. R1 pings ISP-A successfully and R2 pings ISP-B successfully. Our basic BGP infrastructure is now stable and connected. To improve security and prevent prefix hijacking, we implement ACL filtering. We use configure terminal to enter configuration mode. We then create a standard access list named Skynet prefix, permitting our only specific network 192.168.100. Lastly, we apply this filter to our BGP process. We create a roadmap called filter out that match our ACL. Inside the BGP configurations, we apply this roadmap to our neighbor as an out filter. This ensures we only advertise our authorized prefix to the ISP, securing our routing updates.
Prefix hijacking is a network attack or misconfiguration scenario in which an autonomous system incorrectly advertises ownership of an IP prefix that it does not legitimately control. As a result, internet traffic destined for the real owner of the prefix may be redirected to the hijacking AS, causing traffic interception, data loss, denial of service, or man-in-the-middle attacks. Prefix hijacking can occur either accidentally due to configuration errors or intentionally as a malicious attack. Prefix hijacking occurs in BGP because BGP is a trust-based routing protocol that does not inherently verify the legitimacy of route advertisements. When an AS advertises a prefix, other BGP routers generally accept and propagate the route if it appears valid. If a malicious or misconfigured AS advertises a prefix that is more specific, BGP's longest prefix mesh rule causes traffic to prefer the hijacked route. Since BGP does not authenticate prefix ownership by default, the false route can quickly spread across the internet. ACL-based prefix filtering helps prevent prefix hijacking by allowing network operators to explicitly control which prefixes are accepted from or advertised to BGP neighbors. By configuring access control lists or prefix lists on BGP sessions, a router can permit only legitimate expected prefix from a specific neighbor and deny all others. This ensures that even if a neighbor attempts to advertise unauthorized or incorrect prefix, those routers are filtered and not installed in the BGP table. As a result, ACL-based prefix filtering significantly reduces the risk of both accidental and malicious prefix hijacking and improves overall routing security and stability.